let's learn let's discuss what's reinforcement learning at the highest level. So in general, in machine learning, we usually consider three main pillars of machine learning, right? That would be the supervised learning, unsupervised learning, and reinforcement learning. So in order for us to be able to distinguish between the three pillars, let's quickly define what would be a learning task in each one of these classes. So for supervised learning, the training data is usually composed of pairs of x and y's, what we call x and y's, which are, the x's are considered as the observations. So this can be, so each training data might include one observation vector, one x, and this vector might include many features, right? So a single x is might be a long list of features. And y would be the label, the value that is assigned to this feature. So for instance, x can be an image, any image, so that would be just a matrix of pixels, right? So it's just a large matrix of RGB values, and these are the x vector or the x matrix in this case. And of course, right, a matrix, you can always flatten it to be a vector. At the high level, it is the same. And the y, the label can be if there's a dog or a cat in the image, right? Yes or no, a dog or a cat. Right? We just need to determine that. And so the goal for supervised learning would be to learn a function that maps x's observations into labels. Right, so we can train it to, to classify images, whether it shows a cat or a dog. The applications include classification, regression, classification where we would like to understand or to assign a label out of a set of labels to each one of our observations. Regression, where our label is actually a continuous value. Object detection, for instance in an image, semantic segmentations, image captioning, and so on. There's many applications. Okay, in any case, that's not the main topic of this course. You just need to understand that actually we will use some supervised learning techniques later on when we discuss deeper RL, but for the sake of this course, at least you need to be able to differentiate between the different classes of machine learning. Next, we have unsupervised learning. Here we are only supplied with training data. This will be just the x vectors, so only observations, no label. The goal would be to learn some underlying hidden structure of the data. And the applications for unsupervised learning include clustering, data mining, feature extraction, density estimation, and so on. We might use, and maybe for your project you might use several of these several such techniques, mainly for feature extraction. So feature extraction techniques can be very relevant in reinforcement learning. We'll discuss that later on down this semester. And finally, we have the reinforcement learning pillar, where the training data will be interactions with the environment. And our goal would be to learn a policy, which is a mapping from states of the environment to actions. And we need to learn a policy that maximizes some utility function that is given to us. Applications include robotics and automation, text, speech and dialogue system, resource management, and many applications that we'll see throughout the course, right? This is the main topic that we're going to cover in this course. Okay, so let's look at a quick example, and hopefully an intuitive example. So we have a dog here that is trained to sit whenever it is instructed to do so. And the first question that you should ask yourself would be, how does the dog learn to sit when it is instructed? Or more specifically, what are the key capabilities that are required to perform such learning? So, Webhub, what would be the relevant, the key capabilities that are required for the dog to do such learning?
I don't know.
What's your best guess?
I teach my dog through treats. Maybe it needs to be hungry so that it'll eat my treats.
So, but hungry is not a capability, right? So, what the dogs need to be able to do, to perform, or to to sense, I would say, in order to learn, to do the learning, right? So I'm asking about the capabilities that are required in order for the dog to learn how to sit when instructed.
Mm-hmm.
So the dog will need to be able to sense, because the dog sits whenever it is instructed to do so. So it needs to be able to hear that this instruction,
Mm-hmm.
right? So the dog needs to be able to sense when the state of the environment changed.
Yes.
Next, it needs to be able to act, right?
Yes.
It
That
will be
makes
able
more
to
sense.
learn to sit down only if it will be able to actually try and act and sitting down and see what will be the outcome of that sitting. And then finally, how can it understand that sitting is what it should perform whenever it's instructed to do so?
Because I give it treats.
A treat, right?
Yeah.
So this will be exactly the utility evaluation, right? This is what we say by a utility function, or the ability to evaluate the utility. So the dog needs to understand, hey, I'm getting a treat. I did something well in a good way, right? I did something well, and that's very important. So if the agent can sense, and then can sense the environment, can somehow change the environment, and then can evaluate the utility of the new state, these are mostly the capabilities that we say should be required in order to perform reinforcement learning.
That makes sense.
Good. I'm
you.
happy. Okay, so the basic and the idea for a reinforcement learning agent, whether it's a dog or a computer in this case, mostly in our case, is as following. Our reinforcement learning agent receives feedback in the form of a reward. So this will be known as a reward function. And our agent's utility is the sum of these rewards. Okay, so the agent should learn to act in a way that maximizes the expected sum of rewards. And the learning is based on the observed actions and outcomes and these rewards. So for instance, if we have this example on the right here, which is an agent. So this is my right? I'm not sure in the recording. So sorry, this should be in the left in the recording. In my slides, it's on the right, but in the recording it's on the left. So the example here on the left shows you the reinforcement learning agent, in this case in the form of a computer, and the environment, let's say it would be autonomous driving. So the agent needs to be able to sense the state of the environment, what's going on around, or the relevant features that are relevant in order to make a good decision, a correct decision or an optimal decision. So our agent senses the state of the environment. Then it performs an actions that changes the environment. Okay, so it can steer the car left, right, stop, go forward, anything like that. And then we assume that it is able to sense some type of a reward. It was in a specific state, it performed a specific action, and then we need a signal telling it, hey, listen, this action was positive in general, you got to a positive outcome, or it resulted in a negative outcome. You crashed into another car, for instance, right? So the reward function will be dependent on that. And this is exactly what we said earlier with the dog, the state, the ability to read in or to sense the state that is analogous to the ability to sense the environment. The reward would be our computational of utility, and the action is the agent's ability to actually influence the environment, to change the environment.